So texture is a pattern on the surface. It's difficult to give a general definition of texture actually. People have been struggling with that quite a bit. We won't make an effort to have a nice mathematical definition of it. But probably you have an idea of what texture actually means. It's the pattern on the surface, like this stonish pattern on the word. Here are some examples of different textures. And you can start to think of features by which you can describe them. Here's some intuitive examples. For instance, say, okay, the texture on the left is quite oriented. We have these dominant orientations, horizontal and also a bit vertical. Whereas here there's no really dominant orientation at all. So these clouds have all kinds of orientations for their edges. So that would be a rather oriented texture, and that's a more isotropic texture, meaning all the orientations are equally present. Okay, so the level of orientedness could be a first kind of characteristic by which we try to describe a texture. Here's another one. The pattern on the left is far more regular than the pattern on the right. This is more like a stochastic pattern, more random. And this is a highly ordered pattern, very regular. So that would also be one of these more intuitive characteristics by which to describe the textures. Or you say the one on the left is pretty coarse and the other one on the right is more fine. You see that the basic unit here is this kind of block here is pretty big, a basic unit here is just a small piece. So another kind of characteristic. Right. So, and most of the texture features that we will describe have aspects of all those characteristics in them. And here are the features again that we will describe for texture analysis. We have Fourier features based on our good old Fourier transform, co-occurrence matrices, filter banks, and then stochastic model we forget about. We have no time for that. So the first, the Fourier features. Okay, so what do we do here? Remember, if we do a Fourier analysis, we in fact say how much energy there is for different frequencies in different orientations. Because we're dealing with these 2D patterns now. We have orientation in addition to frequency. All nicely summarized in this power spectrum. So for the different frequencies, horizontal frequency U, vertical frequency V, we can measure how much energy there is in there, and we can average that out in a certain environment. And this would indeed seem to be a good kind of feature, because the previous intuitive properties have very natural counterparts in this power spectrum. For instance, we talked about regularity or periodicity, if you want. Well, if you have a periodic pattern, the underlying frequencies representing that periodicity will have high energy in our pattern. So we have peaks in the power spectrum for a periodic texture. We talked about coarse versus fine. Okay, so if you have a coarse pattern, you will have more energy in low frequencies. If you have a very busy pattern, a very fine pattern, you have more energy in the higher frequencies. So again, something that will seem to come out rather naturally from the power spectrum. We talked about orientation, oriented or isotropic, as we call it. So if you have strong orientation, the trigonometric functions with that orientation will have high energies compared to the others. So again, in this case, sine patterns, they each have an orientation, and the ones with the orientation of the dominant orientation of the texture will have the higher energy. So everything seems to be very well represented by this power spectrum. That is also fine. So which features have people been proposing from the power spectrum? We cannot simply start analyzing all the numbers in the power spectrum. That would be a huge vector. No, we summarize them. And here are two examples. For instance, we take in this UV space, for the power spectrum, we take a ring, and within that ring we sum all the energies. So we integrate the power spectrum within the red ring that we have here. So you have that's an inner and an outer radius. That's one type of feature. We can do that for different rings. Okay, we can take this ring, a smaller one or a bigger one around that, and for each of these rings we can define such a sum. Alternatively, we could look at this kind of wedge pattern, kind of a tie, if you look at this here. So it's going a certain orientation and a small area around it, summing all the energy for those orientations. And indeed, those features can be expected to pretty well capture things we have been talking about. Like in this case, coarseness. If the smaller rings have more energy than the wide rings, lower frequencies have more dominance over higher and you have a coarser texture. Or in this case, that will have a lot to say about the directionality, the orientedness of our texture. If there's a certain dominant orientation, that wedge will have a lot of energy. Okay, so Fourier features seem to be actually very well suited. Now, that also came out to be true. You can use these Fourier features with good effect, with a high performance, but there is a problem, and actually a huge problem for most practical applications. And that is, if the entire image does not consist only that single texture, but multiple textures, like you have a remote sensing image, and you have all these different fields with different plants and crops on them, different textures resulting, the Fourier analysis is not appropriate. The problem for a Fourier analysis, once you have more than just that single texture in your image, is that it is a global transform. It collects information from all over the image. It is not localized at all. These sign functions, these trigonometric functions that underlie the Fourier transform, have an infinite extent in principle. They cover the entire image. So no localization, that is the issue. So as soon as you have more than one texture, you would want to segment different textures and describe the individual textures. It's a problem. You don't get there. The Fourier transform does not allow it. It's global. The Fourier transform collects information globally over the entire image and therefore is not good for segmentation or inspection. Inspection indeed also being often a localization problem, because in an entire texture you may have a little spot here which is wrong, and therefore you would like to detect. The problem with the Fourier transform is it collects information from all over the place, so probably the information from that small erroneous spot gets just buried by information from all around. So it's not good in localization, detailed detection at all. Okay. That brings us to the next kind of feature, because now we want to introduce some information about localization. Okay. Therefore, co-occurrence matrices have been used. It's about the distribution of different intensities. Remember we saw the histogram, or you know about histogram probably. So that gives a distribution for different intensities. So for every intensity, you know how many pixels come with that intensity. That's a 1D distribution over intensity. This is a two-dimensional distribution. And also compared to the 1D histogram, in fact it adds some information about position, although still weak, but it has some information about position at least. Okay, so what are we talking about here? So, okay, suppose this is the input image, and that would be its histogram. So for all the different intensities along the abscissa, we count the number of pixels or the percentage of pixels having those different intensities. But we don't know where these pixels are. So just like a Fourier transform, a histogram of intensity carries no spatial information with it. And that we want to change. And we stick close to the idea of histogram. This is kind of a histogram, but with a little bit of spatial information added. So what do we have now? We are not looking at individual pixels anymore, but rather at pairs of pixels. Pairs of pixels that are connected by a fixed vector. So, for instance, here we have these 2 points, these 2 pixels, say. They come with their intensity I and J. So J would be intensity of that pixel, and I for that pixel. And the relative position is fixed. So we have selected that pair to have a certain relative position specified by this vector, the red vector. And we keep that fixed. And then we move that vector across the entire image. And we read out tail and head at every position. And then we start to fill up a matrix. It starts with 0 everywhere, and then every time we find a combination of tail intensity I with head intensity J, we will increase the corresponding position in the matrix column I and row J by 1. We increment. So we do that for all the different vectors across the image. We look at the pair of intensities and increment the corresponding position in this matrix. So again, it's a distribution concerned with intensities, but about the pair of intensities rather than intensities in single pixels. By the way, the resulting co-occurrence matrix as dimensions number of intensities times number of intensities. And it has a little bit of spatial information because we now added the constraint that this pixel pair had to be at this relative position. So if you choose another vector, another relative position, we get a different co-occurrence matrix. Here are some examples. It's a textile, by the way. Here we get the same textile twice, but with a different vector. So that would be the vector that we just defined, specifying the relative positions of head and tail pixels. And here we have a different choice for the vector. And note, this is pretty much a periodicity vector. And this vector by no means corresponds to a period of this pattern. Here are the corresponding co-occurrence matrices. This for that image and this co-occurrence matrix for that image. Now, by the fact that we have chosen more or less a period for the first vector, the head and the tail will typically fall on similar pixels, same kind of position but in a different period. And therefore, the 2 intensities are pretty much the same. The result is that the co-occurrence matrix will be more like a diagonal. The tail intensity I and the head intensity J are very similar. If they would be identical, then you would of course have to increment the position on the diagonal of the co-occurrence matrix. But black here means 0 and bright means higher. It's a bit difficult to see. The contrast won't be so good. But the only thing I want you to pick up from this example, first of all, you don't have a perfect diagonal matrix here because also the periodicity is of course not perfect. These periods change a little bit from one to the next. But the second thing is that if you have a period, you get this kind of clustering of high values around the diagonal, an effect you don't have if you take a vector that's not a period. Here you have values far more spread over the entire co-occurrence matrix. So you see that the choice of Fred vector, relative position vector, has a huge effect on the resulting co-occurrence matrix. Here it's the same as before, so if you now want to use some features to classify, we already said with the power spectrum of the Fourier transform, it's difficult to use the entire power spectrum as a huge vector to put into a classifier to, for instance, say which is the texture. Here the same, right? So an entire co-occurrence matrix is really a lot of numbers, and the question is whether we need all of them to then classify, for instance, a texture. In practice, people will use a limited set of features. Well, very well known are the so-called 14 heraldic features after the person who introduced them first. But we won't go into all of those. Here are just some examples. They come from that heraldic list, actually. For instance, here we have energy. It is a sum of the squares of all the entries in your co-occurrence matrix. If your matrix is more diagonal, you will have a much higher value because then you square very large numbers around the diagonal. If it's more spread out, the values will be lower everywhere, you get a lower value. Also very interesting is, for instance, this one, contrast. It measures the amount of energy, the responses, the entries away from the diagonal. So the further you go away from the diagonal, the more I and j will be different, and the more contributions you get. So if you have a very spread out matrix, it will get a higher contrast than if you have a more diagonal matrix. If it's pure diagonal, it gives even 0. So you have all those different features. So you get a feature vector. You have your scene from which you extract your co-occurrence matrix after, of course, defining that relative position matrix, relative position vector, sorry. Once you have done that, you get a co-occurrence matrix, you extract those features, that gives you a small feature vector, that can be shifted into a classifier, which then decides maybe on which texture it is. Now, co-occurrence matrices already introduced a little bit of the concept of location, relative location in this case. But often that is indeed not good enough. As we have seen, if you want to, for instance, classify textures in an image, for instance, to segment the different agricultural fields in an aerial image, you need far stronger information that is localized. So people start to work also on filter banks. And filter banks are sets of convolution filters. In fact, the outcome of convolution filters. So you have a set of convolution filters, each of which you apply at all positions in the image. That gives you a feature vector, the output of these convolutions at each of these positions. Typically what is also done is you average out a little bit the energy, so the square of the output in a certain region. That dampens also the sensitivity to the precise location, captures a little bit more of the context, so that's typically good for a classification of the texture. And that way you can segment scenes. Now, what are the convolution filters to use? And here we have a number of them: Laws, Garber, and then eigenfilters as the last bit of this contribution. What are the Laws filters? Well, Laws filters are predefined. So it doesn't depend on the texture, you always work with the same convolution filters. And they are produced as a convolution of a small row filter and a small column filter. So you have these two one-dimensional convolution filters, which you combine into a two-dimensional convolution filter. For instance, these first three vectors, 1, 2, 1, minus 1, 0, 1, and minus 1, 2, minus 1, they will be combined with the same, but then as column vectors. So you would, for instance, combine 1 to 1 with 1 to 1, but then as column vector, with minus 0, 1 as column vector, and also with the third one as column vector. There are indeed, in the end, 9 different combinations. So we get 9 of these 3 by 3 convolution filters from that approach. Notice that we have met quite a few of these filters already. You will see that some of these loss filters are like Sobel edge detectors, or they are like a binomial averaging filter, so take kind of an average, reducing the noise. There are blob filters coming out of that thing. So typically these filters will also give high responses when a certain type of pattern, like an edge or a blob and so on, are present. We can do the same, but then for a larger filter, in this case a 5 by 5 filter, by combining these 5 row filters now with the same kind of column filters, yielding 25 combinations again. So now we have a longer vector, we have 25 convolution filters already. And we can keep on doing similar stuff. We can also use the 7 by 7 loss masks and so on and so forth. So, but they are predefined. You don't care about the texture. You always apply the same convolution filters. So notice these loss filters, they give you simple convolution filters, but actually they are surprisingly effective. So from these kind of features, as I said, typically squared in small environment around the pixel and summed. So the output of a convolution filter is squared, and then that output is summed in a small neighborhood, and that attributed to the central pixel, and you have that for different convolutions. So that kind of feature vectors are sometimes very effective for classification of textures, although the method is very simple.